Okay, section 1.2, algebraic limits and continuity. What we've talked about in section 1.1 was numeric limits and graphical limits. So basically looking at the numbers as they approach the x value, and then looking at the graphs as they approach the x value. Well, maybe we're not always going to have that option. Maybe numerically is going to be too difficult, or maybe we don't have a graph, or it's not easy to graph, or something like that. So there might be another way to do it. Algebraic limits and continuity are what we're going to talk about. So some vocabulary: continuous at a point, continuous on an interval, discontinuous or discontinuity, and then what's called jump discontinuity. We'll get into all that. Okay, let's consider the three functions that are shown here in these graphs. F of x equals x is the first one, g of x equals 3, which is just a horizontal line going through y equals 3, and then h of x is x plus 3, which you can see has a y-intercept of 3 and it has a slope of 1. Notice that h of x is just the combination of f of x plus g of x, because f of x is x, g of x is 3, well h of x is the combination of adding x and 3 together. So we can use the graphs to compute the limits as x approaches 1. Okay, this should not be very difficult, hopefully, to do. I think graphical limits are the easiest things to see. As x approaches 1 of f of x, well, it appears that as x approaches 1 of f of x, we seem to be approaching a y value right there, which is 1. Let's look at the limit as x approaches 1 of g of x. Well, g of x is this middle one here, and as the x values approach 1 from both sides, it appears that the y value right there is approaching 3. All right, well now let's look at, scroll this down just a little bit, let's look at the limit as x approaches 1 of h of x, which is the right-hand graph. Graphically, as x approaches 1, from both sides, it looks like we are approaching the y value right there of 4, which, if you look at it, is really just the limit of 1 plus 3. It's the limit of the f of x1 plus the limit of the g of x1. So that actually does work in this case. So the third limit was just literally the sum of the other two, because the f of x and g of x functions were just added together. So this is one of the many properties that we're going to be able to use for limits. So we're going to run through these, and I'm going to try and at least explain them a little bit, and then we'll use them as we go. The first one says the limit of c as x approaches a is c. C represents a constant in this case. But think about it. If it's just the function, because that's really what this is, this piece right here represents the function. Kind of put that right over top the c there. This represents the function. Well, if the function is just a number, so y equals 5, y equals -7, y equals 3, y equals 10, it's just a horizontal line. So no matter what x value approaches on a horizontal line, the y value is always the same. So the limit of any constant is just the constant. It really doesn't make any difference what x approaches. Okay, the next ones aren't quite as intuitive as that one. The second one says the limit as x approaches a of f of x, notice the f of x is all in a big bracket there, to the n power, is the same thing as taking the entire limit in the bracket of f of x approaching a and then raising it to the n power. So what you should be able to see here is that here the function is being raised to the n. Here the function's limit is being evaluated first, and then the whole limit is being raised to the n. So that's what this is saying here. Ultimately, it's saying it doesn't matter whether you raise the function to the power first, or if you raise the limit after you've evaluated the limit of the function, that whole thing to the power. Doesn't make any difference. Okay, and if you remember that a root is the same thing as a power, so this second one right here with the nth root, it's exactly the same idea. I can take the nth root of the function first, or I can take the nth root of the limit after I'm done taking the limit of the function. It doesn't make any difference which order it's in. Number 3 is very much like the example that we did above. I can add or subtract two functions and take the limit Or I can take the limit of each function individually and then add or subtract them. Subtraction, obviously, the order matters. The order does not matter for addition, but subtraction, the order does matter. It's the same idea for multiplication. I can take two functions and multiply them together, or I can take the limit of each function and then multiply the ends and end up with whatever the multiplication of the limits is. I can do the same thing with division. The big thing about division is, however, that the limit of the denominator, which we call m here, that cannot be 0 because then you're dividing by 0. Anything else that works. And the last property says that if I have a constant being multiplied by my function, well, I can pull that constant out to the front, which is what we do here, do the limit of the function, and then multiply the constant back in. And again, we're going to run through all of these things right here in just a second. Okay, example 1. Use the limit properties carefully to find the limit as x approaches 4 of x squared minus 3x plus 7. Now, we could graph this, we could do it numerically, but we're going to use the limit properties instead. And I'm going to be honest with you, most likely you'll never use this limit property in the way that we're getting ready to do it for something like this again, but at least it gives us the idea. So one of the limit properties says that we're allowed to separate all of the additions and subtractions. So let's go ahead and do that. We're going to take the limit as x approaches 4 of x squared. Then we're going to subtract the limit as x approaches 4 of 3x. And then we're going to add the limit as x approaches 4 of 7. There's more properties to be able to be used. The first one has a squared on it. So what that says is because the function itself is being squared, I can take the limit as x approaches 4 of x and then square the whole thing. That's one property. And the second one, those two things are being multiplied. It says what I'm allowed to do is I'm allowed to take the limit as x approaches 4 of 3 and multiply that by the limit as x approaches 4 of x. And then the last one just says I'm taking the limit as x approaches 4 of 7. All right, so the first one was the property which had the exponents on it. The limit as x approaches 4 of x is just going to be 4. But then I can square that result. And I know this one because I know this limit in particular because we used the graph from the previous page. If you look at that one, as x approaches 4, you would know that the y value also approaches 4. Okay? The next piece, the limit as x approaches 4 of 3. Well, 3 is a constant. So since 3 is a constant, the limit of any constant is the constant. And then we're going to multiply that using the multiplication property by the limit as x approaches 4 of x. So we already figured that one out. We just did that. That was 4. And then the last piece is the limit of 7. 7, again, is a constant. So the limit of a constant is the constant. It doesn't matter what x is approaching. And now we're just going to go ahead and simplify this. So we're going to get, what is that, 16 minus 12 plus 7. 16 minus 12 is 4, plus 7 is 11. So there is our limit. Well, you might have already figured this out, but what it seems like is that using those limit properties, all we really did was we plugged in 4 for everything. If I had plugged in 4 into that function right there, wouldn't we just get 11? That's exactly what we got. So if you have, here's a theorem, if you have a rational function is some polynomial divided by another polynomial, and a is in the domain of that function, meaning it does not give you a 0 in the denominator somehow, or it's not outside of the domain of your function, then all you have to do is you have to plug in a for all your x's and you get a value. Simplest way of saying that is if I plug in whatever my limit is approaching and it gives me a real number, we're done. That's the limit. You're finished. For example, use the theorem above to do this limit. Example number 2. Well, can I plug 0 in for x and get a real number? Well, let's find out. If we were to take the limit as x approaches 0. And if we plug 0 in here, we're going to get 0 squared minus 3 times 0, but that's 0, plus 2. 0 squared is 0, minus 0 is 0, plus 2 is 2. So ultimately what we get here is the square root of 2. Is that a real number? Yes, it's not a nice number for us, but it is a real number, just the square root of 2. So that is the limit. Okay, so the theorem above holds because 0 is in that domain. It actually gave us an actual real number. No problem. Okay, let's try it again. When plugging it in makes sense, let's just do it. So let's find the limit in example 3 as x approaches negative 3 over x squared minus x minus 12 over x plus 3. Again, a rational function. So if I were to plug in 3 into this thing, let's see, I'm sorry, negative 3. Negative 3 squared minus negative 3 minus 12 over negative 3 plus 3. Well, I can already tell by looking at the denominator, we have a problem because the denominator is 0. And on the top, we're going to get, what is that, 9 minus minus is plus, so that's 12. So we're going to get 0 over 0. Let's put an arrow there because technically nothing can really equal 0 over 0, so I don't want to put an equal sign there. Again, that is notational. It's very important that we understand nothing actually equals 0 over 0. It can go to 0 and 0 on the top and the bottom, but it can't equal that. So does plugging it in work? No, that did not work. That does not, however, mean that you don't have a limit. It just means that something else is happening there. We have to figure out whether there is a limit. Well, we can try this algebraically. And because this is a rational function, what we can try is we can try factoring. Okay, so that's what we're going to try and do. Let's go ahead and see if we were to go ahead and factor the numerator of this, because the denominator doesn't factor. So the numerator is going to factor, I think that's going to be x minus 4 and x plus 3. Well, algebraically, if we simplify this, the x plus 3's are going to divide away, and what that leaves us with is the limit as x approaches negative 3 of x minus 4. Well, now this is going to give us a real number, because if I just substitute negative 3 in here, we get negative 3 minus 4, which is negative 7, and that is actually the limit of this thing. Okay, that was probably the easiest way to figure out the limit of this. So what I will tell you is, in general, if you end up with something like that, you are probably going to have a limit, but you're going to have to find another way to do it. Usually, factoring is the easiest way to start if it can be done. Okay, let's move on to the next one. Okay, example 4, find the limit as x approaches 2 of x squared plus x minus 6 over x minus 2. Once again, I can automatically tell by looking at the denominator, if I plug 2 in, we're going to get 0. So the denominator is going to give us 0. What happens if I plug 2 into the numerator? You're going to get 4 plus 2, which is 6 minus 6 is also 0. Again, you would end up with a 0 on top and a 0 on the bottom. Usually that indicates we have a limit. We just haven't been able, we couldn't do it by direct substitution. So let's go ahead and factor if possible. So the numerator is going to factor to x minus x plus 3, x minus 2 over x minus 2. So the x minus 2's will divide out, and we're going to be left with the limit as x approaches 2 of x plus 3. Now I can directly substitute 2 in, and we don't have a problem, and what we get is our limit is 5. Okay, let's do one more example here on example 5. There's no denominator here on example 5, so I can tell you that it probably is going to be fine. Notice that the variable has changed, so what you're plugging 0 into here is for h, not for x. Makes a big difference, so just be careful on the variables. So here we're going to get, let's see, if I plug in 0 for h, that's going to leave me with 3x squared plus 3x times 0 plus 0 squared, but 0 squared is 0. Anything else times 0 is 0, so really my limit is 3x squared. And yes, your limit can be a function. It does not have to be a number. So in this case, our limit was 3x squared. All right, so now we're going to talk about the concept of continuity. Most of us can kind of think about what continuity is just by, generalizing what a graph looks like. For something to be continuous, it should have no breaks in it. It should have no stops in it, no holes, no gaps. Easiest way to think about it mentally. So let's look at the following functions here. The first one on the upper left here is a continuous function. The flow from the left to the right is nice because there's no gap. Now I know where it says -1 there on the y-axis kind of looks like it might have actually put a gap in the function. There's technically not a gap there just because the -1 printed over the top of the graph, unfortunately. On the bottom left, it says you can trace these graphs without picking up your pencil. That was kind of the old way of talking about it. If you can draw the entire graph without having to pick up your pencil, then it's continuous. What you should see on the ones on the right are these are discontinuous functions. The first one has several discontinuities. At x equals 1, actually, the graph has a hole at x equals 1. Oh yeah, okay, I see it. Right there. The graph has a hole there. It actually does have a value. The value is right here, but you can see that there's a hole in the graph right there. Okay, and it also has what is called a vertical asymptote at x equals 2 right here, which completely separates the graph. Okay, so in this case, it actually has two different types of discontinuities. And then in the bottom one, this one also has a discontinuity. Again, you can clearly see that there's a break. This is what is called a jump discontinuity because as you can see, as you approach from the left-hand side of 1, it then jumps down to here to this one as you approach from the right-hand side of the 1. So there's a massive gap in between there. I'm going to kind of erase those things. But what you can see is that there is a jump from here to here in the y values. So that one is a jump discontinuity. All right, so we're going to define these better and more carefully on the next page. All right, so here is the actual definition of a continuous function at x equals a. It's got three criteria, and these are very important because these are pretty much how the whole continuity is defined. Okay, criteria 1. F of a must exist. In other words, there has to actually be a value there on the graph at x equals a. Okay, the limit as x approaches a, so as you come from the left and the right-hand side of a, also has to exist. So the limit of f of x as x approaches a exists. And then the last thing is, and hopefully this will make some sense, those two things must equal each other. The limit as x approaches a of f of x has to equal f of a. Okay, so we say a function is continuous over an interval I if the limit as x approaches a of f of x equals f of a on the interval I. If f of x is not continuous at x equals a, then we say f of x is discontinuous. All right, in other words, a function is continuous exactly where plugging in to find the limit works out. So again, let's look at an example here. In example 6, we have f of x, which is given by the piecewise function. So the piecewise function is x squared minus 16 over x minus 4 when x does not equal 4, and when x does equal 4, the value is 7. It's kind of hard to see, but this piece goes with this, and then the top piece is when x does not equal 4. So is it continuous at x equals 4? Why or why not? That's what we want to find out. Well, in order for us to figure that out, we have to go to the definition. So we need to check the limit as x approaches 4. Well, as x approaches 4, that's the rest of the function. We don't want to know what it is necessarily at 4. We want to know what the limit is as x gets close to 4. Well, again, if I directly substitute in, hopefully I'm not going to write this, but you can see how I get 0 on top, 0 on the bottom. What that means is I'm going to go ahead and try and factor this. Try and simplify it first. So x squared minus 16 factors to x minus 4, x plus 4 over x minus 4. Once again, the x minus 4s are going to divide out, which will leave us with the limit as x approaches 4 of x plus 4. Well, now I can directly substitute 4 in there, and what I get is 8. In order for this function to be continuous at x equals 4, that 8 has to equal the function's value at 4. Excuse me. So let's find out what f of 4 is. Well, f of 4 is the one right here. That's defined to be 7. Well, does f of 4 equal the limit as x approaches 4? No, definitely not. One of those is 7, one of those is 8. These are different. Therefore, f of x is discontinuous at x equals 4. So what we would say is the limit as x approaches 4 of f of x does not equal f of 4. Therefore, that's what these, I did not draw that very well. That's what these little dots mean. If you've ever seen that, that's a shorthand for therefore. Therefore, f of x is discontinuous at x equals 4. All right. Example 7. Is the function g of x given by, again, it's a piecewise function, continuous for all x values? So now it's not just asking for one x value, it's looking for all x values. Well, here's the thing. The first piece, that's linear. Linear functions are continuous everywhere, but this only exists up until we get to x equals 2, and including the 2, right there. So it's continuous all the way up until 2. The second piece, this is quadratic, which is also continuous everywhere, but this is only when x is greater than 2, right there. So the only place that this thing could have an issue is at 2. So what we need to do is we need to check the left-sided limit and the right-sided limit and see if those things are the same. If they're not, for one, it doesn't even have a limit, and then obviously if it doesn't have a limit, it won't be continuous because it's got to have a limit in order to be continuous. So let's check the left-sided limit. Limit as x approaches 2 from the left. Well, the left side is when x is less than or equal to 2. So we're going to check it out in that piece. Well, if I plug in 2, because I can directly substitute 2 in there, we're going to get negative 2 plus 3, which is 1. Let's check the right-sided limit. So as x approaches 2 from the right, that's the bottom piece. If I were to plug in 2 there, I'm going to get, let's see, what is that? 2 squared, which is 4, minus 3 is 1. Okay, so the left and the right limit as x approaches 2 equal the same value. So the last thing we have to check is, because now we know the limit exists, does the function at 2 equal the same thing? Well, the function at 2 comes from this piece right here, because that's where the equal to symbol was. So if I plug 2 into that piece right there, we get 1. Therefore, all of these things are equal. It is continuous. G of x is continuous for all x. Okay, what are we at? About 25 minutes there. Again, I apologize for the length of this. We'll keep it under 30. The last example here says, let f of x be the function defined by the piecewise function given. If f of x is continuous at x equals 5, then what is the value of c? So now it's telling us we know we want this to be continuous at x equals 5. In order for us to figure that out, we're going to have to find the limit, and then we're going to be able to figure out what c is, because whatever the limit is, it's going to be the limit as x approaches 5 of square root of x plus 4 minus 3 over x minus 5, whatever that limit is as x approaches 5, that's also going to have to be the function's value at 5, which is what we're looking for, because that part is this. That's the what is c part. This one is a little bit more challenging algebraically. This is going to take a little bit more time. This one we cannot factor. This is not a rational function on top. Sorry, yeah, it's not a rational function because it's not a polynomial on top. The only way to do this one is to do what's called multiplying it by a conjugate. Because if I plug 5 in, we're going to get on the top there, we're going to get 3 minus 3, which is 0. On the bottom, we're going to get 5 minus 5, which is 0. So what we can do is we can multiply the top and the bottom of this thing by what's called the conjugate. The conjugate is the part of this thing that has the square root in it. It's exactly the same as what you see, except that the sign in between the root and the number here are going to be opposites. That is the conjugate, but you can't just multiply the top of a piece by a number without altering the function, so we have to multiply the bottom by exactly the same thing. Therefore, what's in red there is really just 1. I'm just multiplying the whole thing by 1. So let's see what happens when we multiply by the conjugate. We're going to have the limit as x approaches 5. If I were to multiply this top piece, it's foiling. If I do first times first, the square root of x plus 4 times the square root of x plus 4 is just x plus 4. If I were to multiply the outsides and the inside, I'm assuming you all know what FOIL is, I would get 3 square root of x plus 4 minus 3 square root of x plus 4 gone. And then I'm going to multiply last times last, which is negative 3 times 3, which is negative 9. All right, that's the part I wanted to alter. On the denominator, I am not going to FOIL all that stuff out because it kind of defeats the purpose. What I was ultimately trying to get rid of in all of this is this piece right here. That's what we're trying to get rid of. So I'm going to go ahead and just leave this denominator as x minus 5, but I still have to multiply it, so I'm just going to put the whole denominator in a parentheses. Okay, let's go ahead and simplify now. So the limit as x approaches 5, the numerator will simplify. X plus 4 minus 9 is x minus 5. That's wonderful, because I have this x minus 5 down here that I'm trying to get rid of. This is why I did not FOIL all this out. So now the x minus 5s are going to go away. Don't forget you still have a factor of a 1 on the top there. That's very important. Don't lose that. So we're going to get the limit as x approaches 5 of 1 over the square root of x plus 4 plus 3. Now if I were to plug in 5, I no longer have a 0 in the denominator, so we are good. So this is going to give us 1 over, if I plug in 5, that's going to give me the square root of 9, which is 3, plus 3 more 6. I get a limit of 1/6. In order for this to be continuous, the c value, because that's f of 5, also must be 1/6. So c is 1/6. All right, that was plenty long enough. Good luck on the homework, and I think that's enough.